ways of measuring ocular motility, and but most of the methods are clinical, more subjective, and there is not much repeatability. With that background, I present my paper on measuring eye motility reliably with the help of a computerized ocular motility tester which we devised. The authors are the inventors of the device, and we have already applied for a patent for this device named as ocular motility tester. So this is a list of various methods which have been described historically. Way back in 61, Kestenbaum was the first guy who said that a modified ruler can be used to measure ocular motility in millimeters. And followed by this, there was an article in AJO in 67 where Rist et al. Said that a lateral light reflex test can be used for the same thing in degrees. This was followed by Kushner's paper on cervical range of ocular motility, which he published, and this was followed by a computerized test by Jonathan Holmes from Wilmer, where they took serial photographs and then measured with the help of a ruler. And we presented an ocular motility tester that was a mechanical tester way back in 2010. The only problem with this ocular motility tester was that it was accurate only up to ±1 millimeter. So the current concept is that we used computerized algorithms to assess ocular motility, and this is the old mechanical ocular motility tester which we presented way back in 2010. See, what we do here is you are using a marker at the limbus, and then you tell the patient to abduct the eye and then change the marker, and whatever is the effective motility that you can gain from the ruler. Now this is the only problem is that minimum difference would be at least 1 millimeter. Now this is the computerized ocular motility tester which we have devised. So this was the welcome screen. Now followed by this, what we have to do is we have to take a still photograph. We will have to calculate the IPD, and then we will put per pixel per centimeter variability. So then after doing that, we will tell the patient to look on the right, look on the left, look up and look down. When he looks on the right eye from the center, abduction is calculated, and when he looks on the right, left eye, adduction is calculated. The raw measurements, the raw data will come here. You can see this is a screen recording of the live patient which we did. Now the subject looks up, and then we will change it to calculate elevation and supraduction, and then he looks down. So the device would give raw data which has to be fed into the algorithm because you have to calculate the distance of camera and subject, which can change, and if there are any movements during the acquiring the data, if he moves the head little bit, we have to take those stills, superimpose them, and then get the final data. So our observation was with this ocular motility testing that the device was tested on 20 subjects, age matched, and we found there were two authors. So we did it for all 20 patients. We did it twice, and we found a very good agreement between the two authors. The Pearson's correlation coefficient was 0.91, and this is the data for the mean data for right eye and left eye. This is just a brief of all the data which has already been published. The original article by Dr. Kestenbaum, who suggested that the normal motility is from 9 to 10 for adduction, abduction, and depression, and for elevation he said it was around 7 millimeters. A similar paper based on the degrees was published by Rist et al. In AJO, where he said that each millimeter of displacement from the center should be taken at 7 millimeters. We all know that this is very gross, and it is not really reproducible. Kushner et al. Did a same kind of measurement of ocular motility, but he did it with the head movement, and Holmes et al. Took a photograph, and it was more cumbersome than this. So to aim at accuracy, we devised this technique. The device can measure at an accuracy of ±0.5 millimeters. The device at present can give ductions, but it can easily be made to give coordinates into various gazes, and it can also be used to calculate the ocular motility speed, which will give the saccadic velocity. So with this technique, what future holds is that motility measurements can be more accurate, more precise, more reproducible, and it can help measuring saccadic velocities also. Eye movements can be seen in coordinates, and it can be mapped like visual fields in all the different gazes. So we are no longer restricted to 6 or 9 gazes. We can go to more gazes, and it also enhances knowledge about patients' limitations. By patients' limitations, I mean to say that at this point of time, we really do not have a normative data of what is the real ocular motility. So for example, if a patient is going for a driving skill or for a pilot or for sports, we don't know what exactly do you need as an ocular motility. Also, we do not know what is the normal we know the normal saccadic velocity, but it is a very big range. So we don't know how it helps. So with this, it can be done much easier. So I conclude by saying that a new device to accurately measure the ocular excursion has been tested. The measurements are reliable between the observer, so it is a reproducible device. Reproducible measurements can be given. Thank you very much.